Hello, I'm Alex, and I'm here to present a project on azeotropes. So an azeotrope is a mixture of two or more liquids that boil at a constant temperature and produce vapors with the same composition as the liquid mixture. Because the vapor and liquid compositions are identical, at that point, no further separation by simple distillation is possible. They are like inseparable friends. And this image is a typical example of azeotropes. The next question, of course, is when does an azeotrope form? In an ideal mixture of liquid and vapor, the components will follow Raoult's law perfectly and have an activity coefficient of 1. This is the Raoult's law for an ideal mixture. In a real mixture, however, some components interact strongly or weakly than what Raoult's law assumes. So activity coefficient above or below 1. When the components are more strongly attracted, it becomes harder for the liquid to escape the vapor. And then the opposite happens when the components are less attracted. However, sometimes the components of the real mixture become identical and an azeotrope forms. This is when the mole fractions of both components are equal. For this, a modification of Raoult's law is needed. This is the modification law. Here, the activity coefficient corrects the ideal vapor pressure for real solution behavior. When the two equations are combined, the condition equation and the modification equation, you get the combined equation. At the azeotrope, the vapor and liquid phases are equal. This equation provides the point where that occurs. And one thing that has to be pointed out is that this is not when the activity coefficients is equal to 1 for all components, as then no azeotrope would be possible. On the right, you can see this equation I used for a 2-propanol water system. We can now use this in a sample problem where we use a 2-suffix Margulies model. As you can see, we gathered the equations and the saturation pressure for components A and B, the temperature, and the Margulies parameter. Overall, we're trying to find the azeotropic liquid composition that involves component A. So what we first did was we converted component B over to component A, so we don't have component B in the equation anymore. Solved for the activity coefficients, and then plugged them into the azeotropic equation. And overall, we found out that this means that the azeotropic form a liquid composition of about 56% of the component A.